Good linked perspective to corrosion science. So today he presents his talk title, Why do additive manufactured magnesium alloys corrode faster than their cast counterparts? Please welcome Dr. Blackwood.
I was also asked to say something about my department, and I didn't have much, but I do have a glitzy video that we made that it lasted about 6 minutes, which is longer than I wanted, so I've got a few slides. But it gives a sort of background of our department. It was made for the NUS TV for us last year. I couldn't get it to work. It's a big.
The materials science and engineering department in the US has almost doubled in size from roughly 18 academic staff 4 years ago to almost 40 today. And we are planning to hire at least another 10 academic staff to the department. And the US has recognized that materials are going to be very important in the near future, both from pure academic point of view, but also from societal impact point of view. Many new device concepts and industries require huge advances in materials, and this is a great opportunity for groundbreaking discoveries, spin-offs, and industry impact for the university. The most notable hire for our department was Professor Konstantin Novosel, the Nobel laureate who discovered graphene, one of the most important material breakthroughs over the last decades, in an institute which Professor Novosel was heading, the Institute for Functional Intelligent Materials. Other areas of focus for my department are sustainability, soft robotics, and wearable electronics.
Some time ago, we started our work with the two-dimensional material graphene, but in fact the whole family of two-dimensional crystals, which allowed us to create materials on demand by sandwiching individual crystals into a three-dimensional van der Waals heterostructure. And then we realized that we create very interesting states with multiple phase transitions. So you basically see live materials which are very reactive and very responsive to the external environment. Smart membranes which can actively monitor the conditions of the water stream flow, for example, of the surrounding environment. And we try to work on the neuromorphic computers, creating new memory devices capable of doing those machine learning functions with low energy consumption. We work on the ionic devices, those which can be served as the biotic interface for healthcare application.
NUS Applied Materials Advanced Materials Corporate Lab, the Decoder Lab, was established in 2018 with a mission to develop new materials and complex material solutions. The aims of the corporate lab are to build capabilities for the next generation semiconductor manufacturing, not only in Singapore but globally. We also aim to develop industry-aligned talent, as well as to generate startup companies that are based on the work in the corporate lab.
Well, I work on the interface between nanoscience, materials, and electronics to power next generation devices that involves the use of artificial intelligence. In short, I make AI smarter through material science and engineering. We work on intelligent materials that can sense the environment very well. We hope we can give these materials the sense of the doctor's touch, so that they can allow anybody to immediately have a gauge of how healthy they are through our materials and technology. One of the areas that we are developing is self-repairable or self-healable materials. These materials, they are soft, they can behave like skin. Importantly, they can self-repair just like humans can. By having these technologies involved in the making and processing of materials and devices for electronics, they can allow next generation devices that can heal themselves, even if they are damaged.
So we're interested in how electrons in such systems interact with terahertz and infrared radiation, which is important for many applications. So for example, we can apply this technology for quantum communications, we can look into gas sense, we can look for beyond 5G communications, navigation of autonomous vehicles, and many more other directions.
My research mostly focuses on quantum technologies. In particular, my main project is about linking information carried by telecom photons, the kind of photons that carry information in the telecommunication network, together with superconducting qubits, which are a nice building block for quantum processors.
For many years, my group has been working on the industry closely. One of them in Singapore is ST Engineering on different type of new batteries. These cell batteries can offer much higher energy density in principle. They can also be made at much lower cost. So we are in the process to make this cell battery to be able to recycle for a long time. So this would be a big breakthrough for the technology.
Our lab has been quite extensively working on a new research platform we call electrified chemistry to address the critical issues confronted by our society, from energy to environmental issues. So there's quite a number of the applications we can use based on electrified chemistry in the form the high energy density in the flow battery for stationary energy storage and to the on-demand energy production, and also to we call this electrometallurgical battery material recycling. It's mainly for the waste lithium battery materials. And in our lab, we have been quite closely working with the industry and by licensing of technology, and also they have they're very excellent young people, so they have the idea to have a spin-off commercialize the technology.
My vision for the department is becoming the globally leading department in material science and engineering. It provides the best possible education for our students, and it is a place which nurtures talent on all levels. I also would like to see that our department becomes the go-to place for industry whenever they run into fundamental problems with their processes related to materials or new materials to enable their revolutionary new device concepts.